Hello students, today let us see a new topic, that is work and energy. Work. Adjective meaning of work is quite different from the scientific definition of work. In everyday activity, the term work is used equally for mental work and for physical work, as is clear from the following examples. You may read a book or exert yourself mentally in thinking about a simple or difficult problem. You might be holding a weight without moving. You may be carrying a load and moving with uniform velocity. You may be trying hard to move a huge rock which does not move despite your best efforts, though you may get completely exhausted in the process. In all these cases, according to scientific definition, you are not doing any work. Scientific conception of work. In physics, the term work is used in a special technical sense and has a much more precise definition which follows from the following examples. When a box is pushed on a floor by applying a force and it moves through some distance, work is said to be done. In this case, the applied force displaces the box. When we pull a trolley by applying a force and it moves through some distance, work is again said to be done. When we lift a box through a height, we have to apply force. In this case, the applied force does work in lifting the box. From all the examples given above, it follows that work is done if a force is applied on the object and the object is displaced from its original position. No work is said to be done if any of the two conditions is not satisfied. Work when constant force is acting in the direction of displacement. A body A is kept on a smooth horizontal surface. A force F is applied as shown. This force acts on the body for some time, during which the displacement of the body is S. In such a case, work is defined as follows. Work done by a force on a body is the product of force and displacement of the body in the direction of the force. Work equal force into displacement, that is W equal F into S. Work is a scalar quantity. This means that it has no sense of direction. Unit of work. In each system, unit of work, the equal R. 1 R equal if a force of 1 dyne displaces a body through a distance of 1 centimeter, then work is 1 R. 1 erg equal 1 dyne into 1 centimeter. In SI, unit of work is equal joule. When a force of iron acts on an object, and the object moves a distance of 1 meter in the direction of the force, the work done by the force is 1 joule. Definition of 1 joule. When F equal 1 n, S equal 1 meter, then W equal 1 J. If a displacement of 1 meter is produced by a force on 1 n acting in the direction of displacement, then the work done by the force is 1 J. That is 1 J equal 1 n x 1 meter equal 10.5 dyne into 10 square centimeter equal 10.7 erg. Conclusion. When S equals 0, W equals 0, that is work done by a force on a body is 0 if the displacement of the body is 0. For example, when you push a wall with a force F, then the displacement of the wall is 0. Therefore, the work done by the force F on the wall is 0. When you sit on a chair and prepare a lesson in 2 hours, you may feel tired, but according to physics, no work is done. If you hold a briefcase for 1 hour and do not move the briefcase, then S equals 0. Therefore, work done by you on the briefcase is 0. Work when a constant force is acting at an angle to the displacement. Let us consider a body lying on a smooth horizontal surface. A constant force F acts at an angle Q to the horizontal. The body is displaced through distance in the horizontal direction. Here the complete force F is not responsible to displace the body. A part of the force acting in the direction of displacement is responsible for displacing the body. This horizontal part is F cos Q. Work done in this case is defined as work done by a constant force acting at an angle to the displacement is the product of component of force in the direction of displacement and the displacement of the body. Work equal component of force in the direction of displacement, x displacement. W equal F cos theta into S. That is W equal Fs cos theta. Work done is maximum when force acts in the direction of displacement. Case 1. Work done is positive when Q is acute. This is because cos Q is positive. Work done is maximum when theta is 0 degree. This is because the maximum value of cos theta equal 1. This happens when force acts in direction of displacement. Case 2. When the angle between force and displacement is 90 degree. That is when theta equal 90 degree. Then cos theta equal 0 cos 90 degree equals 0. W equals 0. Some examples where work done is 0 because theta equal 90 degree. Work done by centripetal force. When a stone is whirled in a horizontal circle, then centripetal force acts at 90 degree to the displacement. Therefore, work done by centripetal force is 0. Work done by coolie. When a coolie moves a horizontal surface, he applies a force on the load kept on his head. Therefore, theta equal 90 degree. Therefore, work done by the force applied by coolie is 0. Motion of the earth around the sun. Work done by the centripetal force, which is the gravitational pull of sun on earth, acting on earth is 0 because centripetal force is perpendicular to the displacement. Remember, the displacement is always tangential and centripetal force is always radially inward. The angle between radius and tangent is 90 degree. Case 3. When angle between force and displacement is 180 degree. That is when Q equal 180 degree. Then cos 180 degree equal minus 1. In this case, work done is negative. Let us take an example where work done is negative because Q equal 180 degree. A block A is pushed by the force F and displaced through S. Work done by applied force, that is W equal F into S into cos 0 degree, that is equal Fs. Work done by frictional force, W equal F into S into cos 180 degree equal minus Fs. Next is memorize. Work may be positive, negative or 0 depending on the angle. Energy. When a car runs, the engine of the car generates a force which displaces the car. In other words, work is done by the car. This work is done on the expense of fuel. Fuel provides the energy needed to run the car. Had the petrol tank been empty, car could not be run. The conclusion is that if there is no source of energy, no work will be done. Let us take another example. Suppose a leaf takes some person from ground floor to second floor. Then the lift performs work. If you inquire, you will find that the lift is operated by an electrical motor. Thus, electrical energy does the work. If there is no electricity, the lift will not operate. Again, if there is no source of energy, no work will be done. The above statement is not just true for the above two examples, but is true for all processes. Therefore, energy is defined as the capacity to do work. More the energy in a body, more is the work the body can do. Energy is a scalar quantity. The SI unit of energy is joule. Bigger unit is 1 kJ equal 1000 J. 1 mJ equal 106 J. The CGS unit of energy is air. Memorize. Energy is the ability to do work. More the energy, more the work that can be performed, and vice versa. Forms of energy. Nature has been very kind to us in providing us energy in various forms. These forms of energy are as follows. Solar energy. The energy radiated by the sun is called solar energy. Plants collect and store this energy to make food through photosynthesis. Heat energy. It is the energy released when coal, oil, gas or wood burn, and it produces in us the sensation of warmth. Light energy. It is the form of energy which produces in us the sensation of light. Sun is the natural source of light. Chemical energy. It is the energy possessed by fossil fuels, that is called petroleum and natural gas, and is also called the fuel energy. The food that we eat has chemical energy stored in it. Hydro energy. The energy possessed by water flowing in rivers and streams is called hydro energy. This energy is used to generate electricity in hydroelectric power plants. Wind energy. The energy possessed by moving air is called wind energy. Ocean thermal energy. Solar energy stored in the oceans in the form of heat is called ocean thermal energy. Geothermal energy. It is the heat energy of the earth and is found within rock formation and the fluids held within those formations. Biomass energy. It is the energy obtained from biomass, that is, living matter or its residues. Tidal energy. It is the energy derived from the rising and falling ocean tides. Sound energy. It is the energy possessed by vibrating objects and it produces in us the sensation of hearing. Mechanical energy. It is the energy possessed by a body due to its position or motion. The energy possessed due to position or configuration is called potential energy, and that due to motion is called kinetic energy. The sum of these two energies is called the mechanical energy. Electric energy. The energy possessed by charges either at rest or in motion is called electric energy. Magnetic energy. It is the energy possessed by magnetized bodies, example a magnet. Electromagnetic energy. It is the general name for electric and magnetic energies. Nuclear energy. The energy produced in the process of fission and fusion is called nuclear energy. First one is kinetic energy. A moving object is capable of doing work because of its motion. Hence, we say that the object has kinetic energy. Kinetikos in Greek means to move. Hence, kinetic energy means energy due to motion. The energy is stored in the object when work is done to change its velocity from a lower value to a higher value or from rest to certain velocity. Kinetic energy of an object is defined as the energy which it possesses by virtue of its motion, and is measured by the amount of work that the object can do against an opposing force before it comes to rest. Kinetic energy of an object moving with a certain velocity is equal to the work done on it to enable it to acquire that velocity. Examples of bodies possessing kinetic energy: a ball rolling on a surface because it can set another ball into motion by striking it; a bullet fired from a gun, as it is able to penetrate some distance into a target which it strikes; a torpedo in motion, as it can do work by penetrating into the side of a ship; water in motion, as it can turn a wheel or a turbine; a fast wind, as it can set a boat in motion when striking against its sail; a moving hammer, as it drives a nail to a wall against the resistance offered to it by the wall; a falling body, as it can break something on which it falls. Expression for kinetic energy: consider an object of mass m which is moving with an initial velocity u on a perfectly frictionless surface. Let a constant external force F act on it and produce an acceleration A in it. If v is the final velocity of the object after having undergone a displacement, then from v square minus u square equal to as, s equal 2 minus over 2a, work done by the force in displacing the body through s, that is W equal F into S. We know from Newton's second law of motion F equal ma. From equation 1, 2 and 3 we get W equal ma in, or W equal lower 2 mv square minus lower 2 mu square. If the object is initially at the rest, u equal 0, and as such from equation W equal lower 2 mv square. This work done in making the object acquire a velocity v after starting from the rest has not gone waste and is in fact stored in the object. Work stored up in a moving object is called the kinetic energy of the object. If kinetic energy of an object is denoted by Ek, then Ek equal lower 2 mv square. Kinetic energy of a moving object is defined as half the product of the mass of the object and the square of the speed of the object. Potential energy: the energy possessed by an object by virtue of its position or configuration is called its potential energy. It is measured by the work that the object can do in passing from its present position or configuration to some standard position or configuration known as zero position or zero configuration. The kinetic energy of mass m converts into elastic potential energy of spring. Let us take an example. Let a small mass m be released from a smooth inclined plane. Another mass m is kept at a rough horizontal plane at rest. The mass m will move along the inclined plane and strike the mass m. Both the masses will move along the horizontal surface for some distance and come to rest. Thus, potential energy is defined as follows: the energy possessed by a body due to its position or change in shape is called potential energy. Note: the energy possessed by a body due to its height from the surface of Earth is called gravitational potential energy, and that due to change in shape is called elastic potential energy. Other examples where elastic potential energy is stored are a stretched valve, a stretched rubber band, a wound spring. All above examples are because of change in shape. Expression for gravitational potential energy: let us consider a block of mass m kept on the surface of Earth. Let the block be lifted to a height H. For that a force F is required, which is equal to mg. This force lifts the block through a distance h. The work done by this force W equal F into S, that is W equal mg into S, F into mg. This work is converted into potential energy of the block, that is P equal mgh. The expression shows that potential energy depends on mass m, height h from ground, acceleration due to gravity g. Transformation of energy. We have discussed various forms of energy available to us. We convert energy from one form to another, given by following examples. Conversion of mechanical energy into electrical energy. The potential energy of water stored in a dam is changed to kinetic energy when it falls from a height. This kinetic energy rotates a turbine to produce electric energy. Conversion of electrical energy into mechanical energy. An electrical motor uses electrical energy to run various electrical appliances. Example, a train, a fan, washing machine, mixer, grinder, etc. Conversion of electrical energy into heat energy. In an electric heater, a geyser, a toaster, an oven, etc., electric energy is changed to heat energy. Conversion of heat energy into mechanical energy. In heat engines, that is example a steam engine, heat energy changes to mechanical energy. Conversion of electrical energy into light energy. In an electric bulb, a fluorescent tube, a floodlight, etc., electrical energy is changed to light energy. Conversion of electric energy into sound energy. An electric bell, a stereo, a loudspeaker, etc. change electric energy into sound energy. Conversion of chemical energy into heat energy. When fuels are burned, chemical energy gets converted into heat energy. Conversion of sound energy to electrical energy. A microphone converts sound energy into electrical energy. Conversion of chemical energy to electrical energy. An electric cell converts chemical energy into electrical energy. Law of conservation of energy. According to law of conservation of energy, energy can neither be created nor destroyed. It can be converted from one form to another. How is the kinetic energy of a body related to its momentum? Let us consider a body of mass m having a velocity v. Then momentum of the body p, mass into velocity, equal m into v. This gives v equal 1. From definition, kinetic energy of the body equal 1 over 2, that is mv square. Substituting the value of v from equation 1 into equation 2, we can write Ke equal 1 over 2m into P2 over m2 equal 1 over 2 into P2 over m. Then we can write P square equal 2m into Ke, that is equal P equal 2m into Ke. This momentum 2m into mass into kinetic energy. Okay friends, thank you for watching this video. Bye.